Good morning or good afternoon and welcome to today's XP Live webinar. My name is Catherine Tran and I'm part of the marketing department here at the XP Solutions Portland office. So today's webinar will demonstrate the steps involved in preparing data for sanitary sewer modeling. So if that's a topic that you're here for, then you're in the right place. So one more note here for those of you who may not be familiar with XP Solutions, we have a long history of providing high-performing software solutions. So our intention is to make sure that in your work you can model with confidence. This means that we strive to provide excellent customer service and support and that we offer continuing education opportunities like these for engineers in our industry. Today's presenter is John Howell. John, who works out of Huntsville, Alabama, has 25 years experience in the modeling and simulation world. Prior to joining XP, he worked with both Wallingford and Bentley software companies, but before that he was involved with commercial software for computational fluid dynamics. So thank you all for joining us today and welcome, John.
Thank you. Thanks everybody for attending today. Today's presentation is going to cover a variety of topics related to the data required for modeling sanitary sewer systems. I know a lot of you probably model dedicated sanitary systems and combined systems as part of your work. This presentation is going to concentrate a little bit more on sanitary systems, although elements of what we discussed today would apply to both. The reason I wanted to segregate the discussion of just preparing data for sanitary systems is because of the sensitivity for dedicated sanitary systems that dedicated sanitary systems have to rain-derived inflow and infiltration more so than a combined system where we have flows, a wide variety of flows entering the system. But before we get started today, I wanted to start a poll to ask you about your experience in modeling. Launch the poll now, and if you would be so kind to give us an indication of your modeling experience, we'd appreciate it. Similarly to the first presentation we gave today, it looks like about almost an even split between those of you who use software to model sanitary systems, both sanitary and combined systems, and about a third of you are not currently using software to model either type of system. Wait a few more seconds and then I'll close the poll. Okay, I'll close the poll now. The elements of a sanitary system model, I've broken it down into 4 categories. You may conceptualize it a little bit differently, but of course we have the geospatial data. These are the elements that are in the network. These are the pipes, the laterals, the pumps, all of the things that exist physically in the network, in the sanitary system network. The second item is system demand. So these are, or loads. My counterpart, Tony Cooch, pointed out to me earlier that in sanitary modeling we just typically say load, but I didn't change the slide. So the system loads are the natural diurnal patterns that we see in a sanitary system through household or industrial or use at retail centers or what have you. Then there are the other demands and loads that are placed on the system, and these can come from groundwater or infiltration, dry weather infiltration, and wet weather events that cause additional infiltration. Then there are the operating parameters for the system, so the set points for the pumps and things like that. Those are all the elements that go into a model. It's really in terms of the time step that we use to model a sanitary system. There's, of course, 2 types of sanitary models. We can use a steady state model, and typically steady state models are used for design work or master planning or capital planning, and they're typically concerned with assessing an extreme condition or whether some aspect of the network can handle X amount of flow, for example. So I'm sizing a pipe and I just want to find out if it'll, on its own, if it will be able to accommodate 14 cubic feet per second of flow, or whatever the parameter is. And steady state models are designed to give us a snapshot of the system at some point in time. So typically it's used on the design side of the house. Advances in computers over the last 15 years have allowed us to greatly expand the type of transient analyses that we do, the unsteady hydraulics of a system. So we can now model things like pump cycling. We can model the storage in a system, and storage is less of a concern, of course, in dedicated sanitary networks, but there still can be storage. So we want to evaluate how that storage reacts over time as it surcharges, and then as that flow is directed back into the hydraulic network as capacity becomes available. We can look at continuous simulations using transient analyses. So these are long-term weather events that we might want to look at. How does my system perform over a month or even a year? Continuous simulation is a little bit of a misnomer. A 12-hour simulation can be a continuous simulation of sorts, but it typically refers to events of long duration. And naturally, we want to use transient analyses to evaluate the impact of significant wet weather events. This is probably the most useful aspect of transient analyses, is looking at the combined flows on the system and making sure that we have the capacity to handle certain types of extreme weather events. We can apply a sanitary model in a number of different ways. We've already talked about a couple of them. As we design a network, we typically start modeling up front. For most of you, since you live in established municipalities and you work for an established utility, or you work for a services firm that is doing work for a utility, most of the design has to do with expansion of your network. But you still might want to evaluate some subset of the network. We can use models for long-range master planning, capital planning, rehabilitation studies. Models are now being used in a lot of advanced ways in terms of repair and replace methodologies. So we want to look at the degradation of assets over time, or their performance over time, and model how that changes and base our rehabilitation strategies on that. Asset management is one I didn't list here, but it probably belongs here. It's just an omission on my part, but we're starting to develop much more formalized and intricate asset management plans to wring the most value we can out of our system. We can look at operational problems. Is this pump sized correctly? Do I need to modify the network in some way based on issues I'm experiencing? We can use models for regulatory compliance. Those of you who have the misfortune of using models to comply with a EPA consent decree are probably familiar with that, but it's mandated in certain cases. So modeling around consent compliance programs, it can be pretty intense. We can use modeling to look at what-if scenarios. What if my city grows 2% over the next 3 years? Am I going to have the capacity to handle that growth? What if I replace or what if I abandon part of the network in an area that's seeing less and less use, such as an industrialized area that's entering a transition period or going into disuse? And finally, of course, capacity analysis. Can I handle the loads on the system? What type of data is required for a sanitary model? Well, of course, the network layout, the system data. Most of you are going to have data, or hopefully you'll have data in a GIS, and that's the type of data, of course, that can be read into a program like XP Swim with a few mouse clicks. So hopefully you'll have it in shapefile format, and you just read it in with a couple of clicks. But that might not always be the case. You may have it stored in an asset management system and need to bring it in, import the data, and condition the data before you start to build a model with it. Other required data are the system loads. Typically, we're going to get this from our meters. You know, the basic system load, the dry weather load, should be, we hope it's very close to an aggregation of the meter data in our system. If it's significantly higher than that, then of course we've got some something else contributing to the flow that we need to investigate. Other required data are the hydraulic properties of of the objects in the network, and we'll discuss those more as we go through the presentation. Again, we need the dry weather flow. We need to characterize inflow and infiltration that occurs sometimes during dry weather, but typically ramps way up when we have wet weather events. We need the operational data for the objects in the network, again, the set points for the pumps and things like that. We may also have calibration data that we need to use to make the model more accurate. If we run our analysis and we add up all the loads on the system, but we're seeing a different result, then obviously we need to calibrate the model to align it with what we're actually seeing. And calibration data is something we would get, you know, as a total load on the system, probably measured at the end of the system, the treatment plant. And of course, we're going to need weather event data. Network data, we're going to need, as I discussed before, hopefully we're getting it from a GIS, so the coordinates are already there. It's already geo-referenced if it's coming from a GIS. And we'll need the location of all the pumps and appurtenances, as well as the conduits. We'll want to understand the pipe connectivity and the lengths of the pipes, the diameters, invert and manhole elevations, and then the last two I kind of added in. We want to understand the pipe material. We typically, you know, we understand what the roughness value is for a given material because we've gotten it from an engineering document or a manual. But we want to put that in the model, and we'll discuss why later. But if we can get the information, we want the date of installation as well. That can help us as we model the system. Where do we get the network data? Some of it we might have to get from maps, either paper or CAD. And if we only have the data in paper drawings or in CAD, then we're going to need to augment that data as it comes into the model. We might be getting the data from construction or as-built drawings. So again, that's something that we'd have to draw by hand as we model. Typically a situation we want to avoid, but sometimes we don't have the choice. Optimally, we'll get it from a GIS system where everything is already geo-referenced, and hopefully a lot of the values that we talked about earlier are also stored as in the GIS system. So it's just read in when we bring it into the model. But again, sometimes we don't have that luxury, and we might have it stored in some other ODBC compliant database or an asset management system. It might come from a work order from the field or a field survey or in spreadsheets. So it's important, I think, for any tool that we have, that any software that we're using for modeling, that software have utilities for manipulating this data as we bring it in. So we'll look at XP Swim. Is what we're looking at here, but similar tools exist in InfoWorks or Sewer Gems. We want to make sure we're using a modeling platform that allows us to work with external data. So some of the tools that are needed are the ability to bring in data from a variety of sources and then map that data to the database in our modeling platform. So it's important, I think, to understand why an investment of this type is needed if you're going to be doing a lot of modeling. I'm not knocking the freeware that's out there, but they just don't have the commercial tools that software like XP Swim has for bringing in external data. And lastly, again, I just wanted to stress the importance, if we can get it, of bringing in the pipe material type and the installation date for that. The reason why is because the installation date and material type can correlate very directly to the degradation rate of that asset in the network and make it more sensitive to RDII over time. So if we can bring that data in, it's very, very useful. In XP Swim, let's look at a node here. I'm going to look at the table view for the node data in my model. And I just added these to the table view here, link installation year and link material. And the reason why that's important is I want to be able to very quickly assign different types of RDII based on the asset class. And one of the neat features that, again, that a commercial tool like this gives you is I can very quickly determine information about the asset through the use of things like graphical encoding. So I can encode this model to show me maybe I've got some old clay pipe that's still in the network. I maybe want to show that in red and make sure that I'm classifying using a different RDII model for those assets versus iron pipe or steel pipe as an example. And commercial tools have some of these fancy features that allow you to do that very quickly. And just as an aside, the data I showed you before, rather than having to go into every object and specify a different model, we have tools like this, which is just a spreadsheet view of the network, but these are editable fields. This is called XP tables. So I can very quickly cut, copy, and paste information about the model. In this case, if I wanted to assign a different RDII model, I could paste that to a bunch of different assets at once. So it makes it very efficient and very quick to do. Some of this discussion kind of goes back to, whoops, getting ahead of myself there. What is the system of record in my system? If I'm a modeler and all I do is model, I'm perfectly happy to let the model be the system of record. That's very rarely the case anymore, especially if you're working in a larger utility. You're always going to have these competing interests within your IT world. You might have IT managers that have their set of primary concerns, right? I want the GIS to act as the system of repository, system of record, or I might have one of these formalized asset management systems, and that system should feed the GIS and the sanitary model. Well, it's very important then that we have those commercial tools to swap data back and forth, and the tool I showed you earlier from our software will facilitate bidirectional sharing of data. So as I make changes to the model, I want to be able to very quickly map those changes back to the system of record without having to, copy files and go through some manual or bespoke import-export process. In XP Swim, you can set those procedures up and do the mapping once, and you're done. That way, when you're through making changes to the model, with a few mouse clicks, you fed that data back in to these other elements of your IT infrastructure that need to share that data. But it's something that we need to think about as we model is what are the other stakeholders in my system, and how do I make sure that the information is consistent amongst the different platforms. Other information that we want to consider is the hydraulic properties. So for my pipe data, I'm definitely going to want to map the roughness. I may need pump curves. I may need flow control information. Where do we get that? Typically, we're going to get it from literature, scientific literature. For some of this, I may have field test data, but more often it comes from the manufacturer or from a contractor submittal if I'm a utility. But it's important that we make this as accurate as we can. Terrain data. You may say, well, why is terrain data important in a 1D sanitary model? It's very important, I think, to have terrain data, whether or not it's just a 1D model. And I'll show you an example of why I think that's important. So I've already read in terrain data here. You can see that as the colored contours. But oftentimes, especially if we're capturing some of the model elements from paper drawings or something like that, and we have field measurements that we're capturing from a field survey or something like that, there may be inaccuracies in the data. Let's say the there's an arbitrary measurement of the length from one manhole to the other. Well, what if that conduit has a really large change in elevation? Well, they may underestimate the length of that conduit. With a geospatial platform like a commercial modeling platform, everything is geo-referenced when we bring it in. So from a bird's eye view, as long as we have the distances specified properly, since this is geo-referenced, the software now knows exactly how long this pipe is. It knows how the distance between these two junctions in the system. So if I'm just entering network elements manually, and I really don't have good information about some of the objects in the network, we have these commercial tools that will allow you to go in and use the underlying elevation to do things like calculate the conduit lengths, calculate the slopes. If I have catchment areas or sewer shed areas, I can automatically determine that from just by drawing them into the model. It'll calculate those automatically. All that's based on the underlying terrain data. We use our platform converts everything to a proprietary format called XP10. But there's a variety of different ways to bring in terrain data into XP-SWIM, and with other commercial platforms, they typically support some methodology for converting existing terrain data into a format that they can use. There is no real industry standard in working with terrain data, which is a little bit problematic, and I would imagine as we move forward in our industry over time, some of these things will be standardized. But commercial platforms like XP-SWIM typically have tools for bringing this type of data in. For XP-SWIM, we can load it from an ASCII grid file or create a DTM from an XYZ file or an Esri grid file, and we have a DTM builder as well. But making use of the terrain data makes it a really quick process to perform global operations on your data to make sure your model's accurate. And it's required, of course, if you're doing 2D modeling. We haven't discussed 2D modeling, and we won't talk a lot about 2D modeling today because overflows are less of a concern in dedicated sanitary systems, but they happen. And I may want to use a 2D model to observe where the flow exits the system and what happens to it. In the old days, we use 1D routing methods to basically proscribe what happens to that flow when it exits the network. With 2D modeling, we let the software determine where that flow is going to go and where it's going to re-enter the network based on the topography. So it's a much more accurate way of looking at overland flow, and we've got to have terrain data if we're going to do 2D modeling. We need flow information, so we know we're going to have dry weather flow, the loads on the system, the daily demands. But what happens to our system when we have a wet weather event? So we're going to have to see increased amounts of inflow and infiltration. We'll need data for that. How do we understand how much is going into the system? Well, there are a variety of different ways. We can look at the meter data at the curb and then look at the total flow and back out how much is coming from wet weather or from groundwater. So there's a number of different techniques to try to estimate what our wet weather flows are, but ultimately we're going to have to calibrate the model based on the meter data that we have and the other flow that we're seeing in the system. The dry weather flows, as far as the data that we need to describe it, we kind of know, we have GIS, so we know the locations. But of course, our dry weather flows are going to follow a diurnal pattern, and typically we'll get that from metering, right? We can estimate that flow based on a number of different things, such as the population that we're serving. We're going to want the minimum, maximum, and mean daily flows for the system, and we can project additional flows based on projected growth or what have you. But sources for that are typically metering. That's about it. Everything else is an estimate. So Meter data is important to understand the exact amount of dry weather flow that we have. And this is just the dialog that we see in XP Swim for base dry weather flow. One of the neat features, I think, for XP Swim is that as we look at dry weather flow, and I'm just going to open up the dialog, the editing dialog for a node here. We want to be able to specify different dry weather flow patterns for different areas of the network. Residential dry weather flow is going to look vastly different than maybe a commercial area. It's going to see increased use on the weekends versus a retail store that's closed on Saturday and Sunday, for example. So we need a way to really dig down and classify the dry weather flows based on the type of area that's being served. Here I just set up a residential dry weather flow. It might look something like this, where I have peak bands in the morning and in the evening, less so throughout the night. If it was an industrial area that runs 3 shifts, that's probably going to have a different type of pattern that's consistent from for the 3 different 8-hour shifts, for example, that occur at that particular industrial facility. But those differences can be really significant. So we want to make sure that we're using tools that allow us to describe dry weather flows differently for different areas in the system. And commercial tools, again, all have these, but it's a real time saver, and it greatly improves the accuracy of the models that we're using. And there's that temporal variation screen that we saw earlier. Another nice thing about a commercial tool like this is I can go in a residential area and say, hey, I anticipate in this zone I'm going to have a 20% population growth over the next 10 to 15 years. I can just apply a multiplier to data that I already have and see what the impact is on the system. Wet weather flows, we can get this information again from rain gauges or flow monitoring, or we can just take a guess at it and define it ourselves, or take a stab at a model and just put something in that we think is reasonable, right? Those are the sources of the data, but we want to assess the impact of wet weather events and how that impacts the network in terms of additional flow. But we're going to get that data from either a design storm or data we have about historical weather events. To me, with the exception of a few design tasks, if we're modeling at all, we ought to be using real-world data for the most part. A design storm, of course, gives us a nice peak flow, and we can evaluate maybe the size of a particular model element based on this peak flow. But if you look at the storm on the left and look at the storm on the right, they're entirely different, and that's especially important. It's especially important in my mind to be accurate in dealing with sanitary systems that accept rainfall derived inflow or infiltration, because that infiltration occurs over time. It has a max, a peak, and then a recession period. Well, it could be a significant amount of time between the time the rain hits the ground and I actually see the additional flow in my network. And we'll talk a little bit more about that. So, I have the first peak here at just past 200 minutes that might actually result in less load on the system than the second peak, because the ground's wet. It takes some time for that flow to enter the network as infiltration. So using real-world events to me is always preferable. Inflow and infiltration, the data that we need for inflow and infiltration, we need a rate for each pipe segment or sub-basin. And again, this is where that material data that we discussed earlier can be important. If we know it's clay pipe that was installed in 1932, we might classify the inflow and infiltration totally differently than for other assets in the system. Of course, we're going to need to know the locations, and then we're going to take a stab at the quantities of inflow. Where do we get that information? From field inspection. If we have measurements, that's great. A lot of us don't have that type of data. We have to take a guess at it. We can look at hydrologic analysis or scientific literature to estimate what these inflow and infiltration rates are. There's a lot of literature out there about it, but each system is going to be unique, and even sub-areas of the system can be unique. So as modelers, this is information that will improve over time as we assess the impact of inflow and infiltration and as we model it. We allow you to use the RTK method to simulate the impact of near-term, medium-term, and long-term inflow and infiltration. And this graphic, most of you have seen this before. So the peak of the initial inflow is always going to be short duration, but we're going to have impacts over time. In a sanitary sewer system, as the ground saturates and flow continues to infiltrate into the network, maybe long after the rainfall event has passed. In our software, this is just the data dialog for describing RDII using the RTK method. This one doesn't, in this example, we don't seek to describe the maximum initial abstraction or initial storage or the recovery rate, but all of those are potential inputs for this model. And of course, we have to associate a rainfall model with it. So the amount of RDII, of course, is going to depend on the weather event that we're modeling. And we may want to change that from month to month. But in XP Swim, we have the option of using a single RTK model, or we can vary it by month. Oftentimes, where weather is not consistent from season to season, we'll want to do that. We need operational data. Where do we get the operational data so that we're accurately modeling our network? Settings for pump operation or settings of flow control devices, data for control strategies or outlet controls. Well, a lot of that data typically resides in the minds of the people that have worked at our utility for years and years. One of the complaints I often hear from utility directors is, my workforce is aging, and they're the ones who actually understand everything, all the operational aspects of my network. So that legacy information that they carry around in their heads, it's important to document that, document their experience and their knowledge, and have a way of retaining that information as people move in and out of our workforce due to retirement or what have you. So not to belabor the point, but interviews with operations personnel are critical in my mind. And then, of course, we want to put that on paper and have records, and then field inspection is another way we gather operational data. Finally, how do we calibrate the model? We need calibration data. So again, we're going to typically get that from field inspection and measurement of recorded depths and rates of flow. We want to keep accurate operations records. We want to document the frequency and location of overflows. We typically have good weather records, right? All of us have access to accurate weather information here in the United States. But we also want to make sure that are we doing enough flow monitoring to understand what's going on in our network? Many times we're not, and maybe there's not as much budget for that as you'd like. But we really need to look at where we can monitor the network to make sure that we have accurate information about what's going on in the network, and we're not just taking a guess at it. And of course, the precipitation data we will get from historical weather data. And in XP Swim, once we have all of this type of data, then we can more accurately assess what's going on in our network. For the same node, I'm going to look at the flow at that node, and in this case, this model has a pump working very, very hard in the background, and that pump is going to shut on and shut off based on the level at a given point in the network. And we can see that that's consistent pattern over time until we get to the actual weather event. So in this case, I've got a 7-day model, and kind of went overboard with this. Probably only needed to run this for about an 18-hour period or 24-hour period, since the weather event is only a 24-hour weather event. But we can see the variation, and it can be fairly significant from a weather event on this particular node. In the runoff mode, we can see the actual impact of RDII on the system and compare that to the rainfall total. As you can see, we have a weather event that's occurring and that peaks here, but the flow in our system doesn't peak until a little bit later. So that's the impact of the rain and the additional flow that's entering our network. We can see the delay here. And as we calibrate the model, we'll take this estimated maximum flow and we'll compare it to actual meter data. And at this point, we might need to make adjustments to our model to to adjust the RDII model so that we're more closely matching the meter data that we get. So there's a lot of calibration that can go on to make sure that we're accurately modeling the impact of inflow, infiltration, the time it takes to get into our system and to have an impact on total flow in the system. So with that, we'll conclude the presentation. I appreciate your attendance today. And again, email me at any time if you have any questions. Thanks very much for attending.